Welcome to the third lecture. And maybe I should really be calling this a lecture series because physically I would span multiple lectures on this topic, the topic of functional analysis. So I also anticipate to produce quite a couple of short videos on this topic. So functional analysis is going to be the mathematical framework, the foundation with which we will analyze the equations that we derived in the previous lecture series. Now this might be a relatively new branch of mathematics to many of you, so we'll go slow and we'll build concepts on top of concepts in a gradual manner. Now the aim of this mathematical foundation is to give us a tangible notions for concepts like stability of a finite element formulation, or the necessary framework and tools for being able to determine if a finite element formulation has a unique solution, if it is well posed. So these are terms that we will develop throughout this lecture series. And the goal thereby is to define concepts like stability such that we can analyze the stability of the equations that we saw before. So in this first video, what I'm going to do is I'm going to motivate this name a little bit, functional analysis. What is functional analysis? And specifically, what is a functional? And the thing that I'll start with actually is to kind of reevaluate our definition of a function. And what I would like to do is to keep things as abstract as possible. So if you think about what a function really is in its most abstract sense, then I would say something like a function is a mapping between sets that associate to every element of a first set one element of the second set. So I think there's a number of abstract concepts that I'm using in this definition. I'm referring to sets here. I'm calling a function a mapping between these sets. And I'm referring to elements inside a set. And I'm doing this on purpose. I think that by abstractifying these things, we're able to do much more than what we would if we would find very specific definitions. Now these abstract definitions though require us to develop some nomenclature in this direction. So let's try and draw what we just said. So I have some starting set. And then my function is going to be a mapping from the different elements. Those might somehow be objects in this set. We're going to map these to a second set, which may be larger, maybe smaller. And then for every element of a first set, we're going to map to exactly one element of a second set. So we're going to take each element, we're going to map that to some element in the output set. Now we could do this for all kinds of things. If we have a farm, then we might associate to any one of the animals on the farm a certain value, and that would be a mapping between sets, the sets of animals, and a set of amount of money, and that would be a mapping between those sets. So that follows the definition that we have right here, and by that definition this will be a function. Right, so this is an abstract notion of a function that kind of encompasses more than just functions like x squared or whatever. So if we have drawn this up now, we can start defining some terms here. So this was our function or our mapping f, and then we call this input set, we call this the domain of f. And let me call this set also x. Typically, if we talk about sets, we give them capital letters to denote them. Now, if we call this the domain of f, then the set onto which f maps is called the codomain. Now notice that if we look at this definition a little bit more into detail, then it only says that every element of the domain has to be mapped onto the codomain. It doesn't say that all elements in the codomain are mapped to. And that kind of gives us another definition here, a definition for all the elements inside of the codomain that are being mapped to, and these are called the image of the function. And my output set I might call, so the codomain I might call y. So if we then write a function also in a very abstract sense, then we would say f in this case is a function that maps from x to y in the way that if we take an element x in the set, well, what are we going to do with this element? Well, we're going to apply f. So this is clearly still extremely abstract, but nevertheless, this might actually be a notation that you've come across before. In the current setting, because I haven't specified x, y, or f, it seems to give very little information. But we can give some specific examples here. So let's do that. So suppose f is this very classical function of x squared. So then, so we're going to just take the quadratic function here. So we have f of x. And we'll use the same notation. So now I'm going to write f of x is a mapping from, well, if I want to talk about the x squared function, where does it map from? Well, it can map any one of the real numbers. Where does it map to? What is its codomain? Well, if I take the square of a number, it's also going to be a real number. So that's the first line of our proposed way of writing functions now. So what would be the second line? Well, we're going to take some function, or so element in R, which we'll call x here, and the operation that we'll perform on R that defines this mapping is we're going to square it. So this would be an example of how you would write the simple x squared function in this notation. Now, there are some additional things that we can say about this, the way that we wrote this right now. One of the things is that I'm using R as my codomain right here. So this is the codomain. This is also the image of f. And I'll give you the opportunity to think a little bit about this question. So in case you want to think about it, you're free to pause the video. In general, I think I'll regularly pose questions, and I would encourage you to pause the video and actually actively think about it. So is the image of f also the complete space R? Well, no, it's not. It's actually only the positive values. So I can take here the image of this mapping f defined as such. It's actually not all of R. It's going to be R larger than or equal to 0, or in a slightly different notation. So this is already a set notation now, where the square bracket denotes includes. and the round bracket denotes excludes. Yeah, so this is really saying we're taking all the values starting from 0 and including 0 all the way until infinity. Now, the thing that I would like to emphasize though in this example, I'm choosing to map a real function or a real number to a real number. Of course, we can also take the square of an imaginary number. The result of that would also be a real number. Or I could choose to define my domain as the space of complex numbers. And then the codomain would also be the space of complex numbers. So that's why there's actually additional information in the notation that I'm using right now, simply more than if I would simply say f of x is equal to x squared. Because then we don't know if we're meaning to map just the real numbers or just imaginary numbers or complex numbers, or we might even consider the input to be functions rather than numbers, and that's something that we'll talk about actually more in just a second. So yeah, I guess the thing that I want to emphasize though is that this additional notation where we're introducing also the domain and the codomain, that is not arbitrary. That is actually important information, and it is strongly embedded in our definition of the function of this mapping. Right? So if you have the same operation but with a different domain or even a different codomain, then it is a different mapping. Okay, so let's talk about another example. Let me define my function like this. So I have f of theta, which is a mapping from, again, all the real numbers to all the real numbers. So codomain is the real number line, and the domain is also the real number line. In such a way that if I take theta, then the operation that I'll perform is, I'm going to take the sine of theta. So now I'll ask the same question. What is now the image of our function f theta? Well, again, its codomain is all the real numbers, but it doesn't mean that it actively maps onto all the real numbers. No, in fact, actually, a sine, of course, only maps on the functions from -1 to 1, including -1 and including 1. So that's why I'm using square brackets for this notation. Now, this was another example where I take a mapping of a number, but that's not necessary. Let's take another example here where we're not actually mapping a number, but rather I'm going to map a vector. So that might be an n-dimensional vector. And I'll map this to the real number line again. And the operation that I'll use is going to be, I'm going to take the vector and I'm going to produce its magnitude. Right, so that's just another example that's also meant to illustrate that this definition that we're posing up here is rather broad. We're not specifically asking a function to perform its action on numbers. It could perform an action on virtually anything. And maybe another one example where we're not mapping onto the real number line, just also give an illustration of something like this. But still within the realm of what we've done before. So let's take another vector, and we're gonna, another vector, and I'm actually gonna move this to the space of n-dimensional vectors. How would I do that? Well, I could do this in all kinds of ways, but suppose that I have a matrix multiplication. Yeah, that maps from n-dimensional space to m-dimensional space. Right, and all of these would count as functions according to our previous definition. So then a lot of our analysis is actually going to make use of the concept of linearity on top of this use of functions and later functionals. So let me pause a little bit and discuss what linearity is. Well, yeah, you might have a very intuitive interpretation of what linearity is, right? So we're probably going to say that this is clearly not a linear operation. This is also not a linear operation. And we're also have been told that this would be a linear operation, and this is not a linear operation. So let's try to specify that. Let's say to think about the definition again. I'm sure you've heard this before, but let's think about this again. So we're going to say that a function is linear if, and there's going to be two conditions. If I take the operation and I operate it on not x but x plus y, then this has to be equal to the operation on x plus the operation on y. And this has to be true for all x and y in our domain x. Oh, you know what? I could actually write this as the domain of f. The second condition is going to be that if I scale my input arguments, so I'm going to take f ax, then it has to be equal to a f of x. And this again has to be true for all x in the domain of f, and also for all possible scalar values. Okay, so I'm introducing here sneakily a little bit more notation. This symbol is something that we're going to see quite often, and this means nothing more than for all. And this symbol is going to mean in the set. Right, so this is saying that this equation has to be true for all x and y in the set, which is the domain of f. And the last statement says that this statement has to be true for all a in the set, which is the real number line, so for all scalar values. Now I could actually compress these two conditions into one, and you would get something like this. F of a x plus y is equal to a f of x plus f of y. And again, for all x and y in the domain of f, and for all a in the real number line. Now, I'm sure that you've seen this before, and this might actually seem like a trivial definition, but now I encourage you to think of about the following example. Suppose that I have this very simple function, f. You know what, I'll give two examples that might not seem entirely intuitive. So I'm going to take f of x is equal to ax plus b. You know what, I'll actually be a little bit more careful in the way that I'm writing this. I'll be a little bit more consistent. Right, so again, f of x is going to be a mapping from R onto R. And it's going to be defined as we're going to take x and we're going to map it to a x plus b, where a and b are arbitrary numbers, scalars. And both of them are real valued numbers. Is this a linear function? And this is probably the classical linear function, but it does not satisfy these two definitions. And I will have you think about why not. But according to this definition, this is actually not a linear function, right? So that's one very unintuitive example of linearity. Right? In fact, this is what we call an affine function. Essentially, this comes down to it doesn't satisfy the second result. It doesn't satisfy this result or this requirement. You can test that quite straightforwardly. Same thing. Can I come up with another example here? Yeah. So What would be a linear function would be if we would take x and would simply map to ax. But suppose now that I'm only interested in, I'm going to define my mapping to have a domain that runs from 0 to 1. Is this a linear function? And in fact, again, it is not. It does not satisfy the first nor the second definition of linearity. Suppose that I take the value 0.5 and a is equal to 2, and then this would be a mapping that maps from no, wait, sorry. Give me 1 second. I'm gonna change my example a little bit. Yeah, okay. So in this case, my codomain is actually equal to my domain, right? Sorry, it's actually equal to the image of f. If I map 0, it's going to be 0. If I map 1, it's going to be 2. So if I define this to be my codomain, then this is actually also the image. So is this a linear function? No, it's not. The example being, if I take 0.5, it's going to give me 1. But if I now scale this by this input by any arbitrary number, it no longer lies in the domain of my function. Well, actually, so in that case, also the previous example that I had was correct. I'll write it down as the third one. So in both of these cases, I am not allowed to do these operations for arbitrary numbers a, nor for arbitrary elements x and y in our input set, right? I'm not allowed to say f of 1 plus 1, because I have said that the domain of my function is only between 0 and 1. And the point that I'm trying to make with that is, again, that the definition of our domain and codomain are fundamentally tied to the function. A function is only linear if also these domains and codomains have certain properties. And that is something that's going to be important later on as well. Yeah, so I think these are a couple of examples that might have been slightly unintuitive, given how familiar we are with the definition of linearity. Then, moving forward, let's ask the next question. So, if this is how we define a function, then what is a functional? And a functional is going to be a specific type of function. A functional is going to be a function that takes a function and produces a scalar. And we tend to use slightly different notation in our definitions of a functional. We tend to write them, so where we typically use the letters f, g, and sometimes h to define a function, or to denote a function. We tend to use something along the lines of an L for a functional. This is going to be now, okay, so this is going to be a function. That means it's a mapping from a domain to a codomain. And in this definition, we already actually know what our codomain is going to be. It's going to be a scalar, so I'm going to map some input set x to R, set of all scalars. And I also know that in this set x, this domain of my functional, we're going to have functions. So in my notation, I might say f, which is now an element of x, is going to be mapped to Well, somehow this functional is going to operate on f, the element of our domain. So this square bracket means acting on. And to be fair, we often simply also write round brackets when it comes to functionals. So although L of f is fine too. So this may be a little funny. So we're taking a function and we're doing something with that, and the result of that has to be a scalar in this real number space. So that means that all the functions for which I can define this operation, or for which I have defined this operation, well, all of them have to lie somehow in this set X. So X is now a collection of a bunch of functions, right? A bunch of these things that we had a couple of examples for here. So we have a whole collection of those functions, we put them in X, and now we define an operation on them to produce a scalar, and that's what we call a functional. So X in this case, so X is a collection or set of functions. And this is called a function space. So a function space is a set of functions. Now again, this is a rather conceptually broad definition. And let's try to specify this, or let's try to make this clear with a couple of examples. So suppose that I have the functional, again, L I'll use, and it's going to be a mapping from a function space, a collection of functions, and the collection of functions that I'll use, I'll write as, so that's going to be x maps to x squared, that's a function. Maybe I should even, officially I should even write this above this, right? And then the second function in my set is also going to be a mapping from R goes to R. And I'll say this is going to be the cubic function. And the third element in this function space is also going to be a mapping from R to R. This is now going to be a fourth order polynomial. And you know what, let's stop there. So this is now a collection of elements, a collection of 3 elements. And each one of these elements is a function. It is a mapping from R to R. And the first one is going to be x goes to x squared. The second is x going to be to x cubed. And the third one is x goes to x to the power 4. And this has to somehow map to the real numbers. And the way that I'm going to define this is I'm going to say if I take some element in my function space, so f, then I will, the operation that I'll perform with f is that I'm going to take f2. And now again, to you the question, what's going to be the image of my functional? This codomain is going to be the complete set of scalar value, so all the real numbers. But what is it? What is its image? Well, again, its image is going to be all the elements in R that it actually does map to. Now, these are going to be, if f is going to be x squared, then if f is going to be x squared, then if I take 2 as an input argument, I'll get 4. And the second potential candidate for f is going to be x cubed, so it gives me 8. And the third is going to give me 16. So even though the codomain of our functional is the real number line, its image is just these 3 numbers. Now let's do one more example here until I'll wrap up. So the second example is going to be L is going to be the set of functions that go from R to R and are defined as x goes to ax, a in R. And this is a functional, so that's the map to the real number now. So I've introduced another symbol here, this semicolon, or this colon, sorry. And this colon means such that, or under the condition. And this is a symbol that we see quite often in set definitions. Yeah, so these curly braces, they denote that whatever is in there is going to define a set. So we have a certain statement here where apparently I've left one variable open, a, and now I have this set for all these possible candidates under the condition that a is a real number. Yeah, so these are all the linear functions. Now, what operation is gonna, this is only the notation in terms of the domain and the codomain, so now I still need to specify the actual operation that L performs. And so again, I have some candidate f in that set, and another example of a functional might be to do an integration. So I'll integrate whatever function is in there from 0 to 1. And that is a much more typical way of thinking about functionals. So the first one was maybe also just a very clear example, but the second one is something that we'll see most of the time. And so the operation being an integration, that's going to give me a real number, and I can perform that operation for all these functions in the domain, and all of them are going to give a real number, and so that makes this a functional. Okay, I think I'll leave it to that for this introduction. Now, functional analysis is again the topic of this lecture series. So what we're going to do is we're actually going to analyze this type of beast, this object. The operation that takes a function and spits out a number. We're going to analyze that, and we'll see that actually partial differential equations, they can also be cast in that framework. And then the question is, when do these mappings produce results, when do they not, and if they don't, that means it's not well posed. Right? So these are questions that we'll be able to answer if we can analyze these functionals and if we're able to cast partial differential equations in this same language. And that's what I'll build up to in the next few videos.